Hello and welcome. My name is Alexander. This is joint work, and today I'm going to present aggregation and garbage collection for online optimization. Let's dive in. So we're looking at online problems, also called dynamic problems, or decompositions of static problems, offline problems, via rolling horizon or sliding window. So let's look at this animation up top here. We have some tasks. We need to schedule them. Time moves forward. Some tasks can't be changed. Some tasks can be changed. And we get new tasks over time. Okay. Well, the size of the instance grows every time new data arrives. We saw that, right? And new data arrives all the time. This will, of course, slow down processing after a long while, right? We will have millions of jobs maybe, and this is going to really slow down processing. Some variables and data are realized, meaning that they will never change. Look at task 1A there. Now look at task 1B, right? Those are completely in that gray zone, which means that they can't change. They are in the past. The past can change, of course. The past has already happened. So there's no uncertainty there, right? And removing all these realized data and variables are not that straightforward in the problem-independent setting, right? It's not that straightforward, unfortunately. So let's look at that, that little graph there to the right. This is the motivation behind this, right? So in another paper, we saw that when we modeled these online problems, if we didn't have any garbage collection at all, the compilation time skyrocketed after a while. But if we had a really simple garbage collection mechanism that was specific to that problem, then we got really good improvement there. So we want to do this problem independently. What are the steps? The steps is number one, identify realized data and variables based on the modeler's input in constraint analysis, right? So this is the problem, this is the little problem specific thing that needs to be there, but everything else is basically problem independent. Step two, aggregate, meaning we summarize the effect of realized data and variables. We do this via model reformulation. Step three, garbage collect. We filter out all data that's left over and not used anymore after this aggregation. And as I mentioned, this is a problem-independent framework. To conclude, this is an important step forward in modeling online problems. What did we do? Well, we are now able to systematically infer realized data, variables, and objects. Modeler provides basic information, but that's all. Now, we also look at how to aggregate common constraints. And a very interesting future work is to create a big library of all these aggregation of constraints. And lastly, we also looked at how to perform problem-independent garbage collection.
Welcome to this 3-minute summary of our paper, Core-Guided Model Reformulation. In this paper, we wanted to address one of the main limitations of constraint programming-based optimization, which is that while many constraint programming models have additive objective functions, CP solvers tend to underperform when trying to prove optimality on these problems. This is because the lower bound on the objective variable is often hard to improve. As an example, we have this simple constraint program here, where a CP solver cannot, without performing some search, find a good bound for the objective variable z. One way we could help CP solvers is to introduce new variables that combine objective terms and provide better bounds for these combinations. And this particular reformulation allows a CP solver to infer that the lower bound on z should be 4. There are, of course, many different reformulations possible, and some are going to be better than others. So in this paper, we wanted to find useful reformulations and try to apply them at the level of a high-level constraint programming model. One approach that does something similar to this is core-guided optimization, where during search, the core-guided solver will introduce new variables and reformulate the objective on the fly to help with solving. So in our approach, rather than going by trial and error, we use a core-guided solver to identify some possible cores, which represent new variables we could add. We try to figure out where in the model these came from, and associate them to some instance data. Then we try to generalize these across several instances. And then we start to modify our model to introduce the new variables and reformulate our objective. In practice, the reformulations that we find have been quite good at improving the performance of lazy clause generation solvers. And in some cases, we can also improve the performance of pure CP solvers. The main contributions of the paper are that we show that it's possible to lift cores from a set of instances to the model itself. Improvements can be found by just grouping sorted terms based on relatedness, and we show that our methodology can help a modeler discover usefully related terms.
Linear programs are solvable in polynomial time, solving large sparse instances can be challenging in practice. For example, instances of basic LP relaxation of weighted CSP originating in computer vision may have millions of variables. To solve such LPs, the classical methods are not always suitable, if only for their superlinear space complexity. We propose an alternative approximate method which can have linear space complexity and is based on constraint propagation. Let us consider the following primal dual pair. Note that any y feasible for the dual on the right is an upper bound on the common optimal value. By the well-known complementary effectiveness theorem, a dual feasible solution y is optimal if and only if there exists an x satisfying conditions 2, which can be seen as a system of linear equalities and inequalities in X. Suppose that we have an initial dual feasible solution. If the complementary slackness conditions are feasible, then it is optimal. If they are infeasible, we can construct an infeasibility certificate by Farkas lemma, which turns out to be a dual improving direction, using which we can improve the current y. Doing this iteratively, we obtain a better and better bound on the optimal value. This is well known in linear programming as the primal dual method. Since checking feasibility of large systems of linear inequalities is costly, we propose to solve it by constraint propagation, which may however not always detect infeasibility. While constraint propagation in continuous variables is known, the novelty is in the fact that whenever we prove infeasibility by constraint propagation, we also construct a certificate of infeasibility in the sense of Farkas lemma, which provides us a dual improving direction. If no infeasibility is detected, we terminate. Note that we may not obtain an optimal solution, but only an upper bound. We show that this approach is a generalization of virtual R consistency algorithm, which approximately optimizes the basic LP relaxation of weighted CSP. We illustrate the approach on the LP relaxation of weighted maxat, for which we define the propagation rules and a memory-efficient way of calculating the infeasibility certificate. The provided bounds are exact for instances of weighted max2sat and non-retractable subclasses. In other cases, the bounds are often not far from the optima of the LP based on experiments using a public dataset. Such approach is in theory applicable to any LP, but the quality of the obtained bounds critically depends on problem structure and strength of the propagation rules.
Hello everyone, hope you're enjoying the conference so far. Welcome to Effective Encodings of Constraint Programming Models to SMT. I'm going to begin with the 3-minute spotlight. Now, in case you're unaware, SMT is an alternate satisfiability paradigm to CP. SMT consists of a variety of different input languages, which are referred to as logics, which different solvers target. The SMT paradigm as a whole draws on a large range of decision procedures and pre-processing techniques, and often you can get SMT solvers which are quite specialized and deploy novel techniques that you wouldn't typically find in the CP domain. So by translating constraint programming models into SMT, we would hope to be able to leverage some of these different techniques and potentially find SMT to be faster at solving some particular problems. So we implemented our translation in a tool called Savaro. Savaro takes the high-level modeling language Essence Prime and translates it to the input of various solvers. Savaro currently supports the CP solvers Minionschaft and G-code, as well as SAT and MaxSat solvers. We implemented support for 3 different SMT solvers alongside 4 logics. Each of the logics came with 2 levels of flattening for a total of 8 encodings. So now that we have our translation tool, how do we know if it's any good or not? Well, we evaluated it against an extensive set of problem instances, and then we compared its performance to a competitor tool, FlatSync to OMT, and then also to the SAT and Chuff backends of Savaro. And what we found is that the virtual best of our SMT backend outperformed our competitor tool's virtual best in both instances solved and in par 2 score. And we also found that the virtual best of the SMT backend outperformed the SAT backend of Savaro and the Chuff backend of Savaro by the same metrics. If you take, however, just the best encoding from the SMT backend, it does not outperform the SAT backend. The SAT backend is still a little bit faster. However, it does outperform the Chuff backend in both of the metrics as well. So we hope that this indicates that the SMT backend performs quite well, and we hope this performance justifies the development of the SMT backend. And we think in particular that the performance of the virtual best demonstrates the value in targeting several SMT logics.